Let's have a look at wireless technology. Wireless technology has advanced so much. It now offers speed comparable to wired connections. Gone are the days when I strictly relied on wired connections for all my devices. Now my laptop, tablet, and TV effortlessly connect to wireless networks, achieving satisfactory speeds. Previously, wireless was primarily used in specific scenarios, such as with stock checking devices or in locations where installing wired cabling was impractical or costly, and it operated at a significantly slower speed. Today, wireless stands as a viable alternative to wired networks in many cases, but not all. Even though I have the option to connect my work laptop to a wired network at home, I prefer using wireless for its ease of setup. In my day-to-day activities, I don't notice any difference in speed, underlying the efficiency and convenience of modern wireless technology. The basic concept of wireless technology involves the use of electromagnetic waves, such as radio frequencies, infrared, and microwaves to transmit data. These waves travel through the air, enabling devices to communicate without direct physical connections. This technology has revolutionized communication and data transfer in the modern world. As wireless has become so common, as a CompTIA A+ certified technician, you will most likely have at least some basic involvement with wireless, and thus it is important to understand. Wireless technologies at their basic level are like a high-tech game of Marco Polo. Wireless devices send out signals like they are yelling out, "Marco!" and another device responds back like it is saying, "Polo." In the case of Wi-Fi, the standards all start with IEEE 802.11. IEEE stands for Institute of Electrical and Electronics Engineers, while 802 is the project number. These numbers are allocated sequentially. Coincidentally, the first meeting was in 1980 in February. For this reason, people assume 802 was named after the year and month, but this is not true. The last part is the sub-project number. In the case of Wi-Fi, it is always 11. Different network types will have a different number. For example, 3 is for Ethernet. The standards define how Wi-Fi devices communicate with each other. The efficiency and speed of wireless data transmission has significantly improved over time. This is largely due to Wi-Fi's ability to utilize a broader range of frequencies than before, along with more intelligent and efficient use of the available bandwidth. While inherent limitations still exist in the amount of data that can be transferred wirelessly, advancements in the way Wi-Fi is transmitted has greatly enhanced both capacity and speed. Nowadays, one of the fundamental parts of a wireless network is the access point. An access point provides connectivity between wireless and wired networks. Essentially, it works as a bridge between the two different networks. Although wireless can be implemented in different ways, this is the most common implementation IT technicians will come across. The access point, often called AP, allows multiple devices to connect to the wired network using the AP as the bridge. This is called infrastructure mode. Infrastructure mode is the most popular way for devices to connect to wireless, but there are a few other ways it can be implemented. Ad hoc networks allow devices to connect to each other without an access point. Ad hoc is not listed as an exam objective or covered in the official training material, so feel free to skip this section if you are only studying for the exam. I will cover ad hoc networks for the sake of completion. Ad hoc networks typically offer lower speeds compared to infrastructure networks, where a central device helps coordinate communication among other devices. The lack of a centralized coordinator makes it challenging to achieve higher speeds. With the increasing popularity of access points and mobile networks, the use of ad hoc networks has diminished as more efficient and convenient alternatives are now readily available. Ad hoc networks typically have a shorter range and lower data transfer speeds compared to infrastructure networks. They also lack the advanced features and security protocols often found in networks with a central access point or router. You may come across the term Basic Service Set, or BSS. BSS is the building block of a wireless network. When referring to infrastructure networks, this includes the AP and the network devices connected to it. To think of it another way, the access point is the central location. The connections between the access point and the devices on the network form a mini-network. This mini-network and its settings are called a basic service set, BSS. When working with wireless networks, multiple BSSs can be combined together to form the one network. Let's have a look. An extended service set, or ESS, goes beyond the A+ exam scope, but I think looking at them helps understand what a BSS is. An ESS is essentially a set of networks comprising multiple interconnected BSSs. Consider, for example, a scenario with two BSSs, or two access points that are part of the same logical network. This configuration enables a user to move seamlessly between the access points while remaining connected to the same network. By understanding this, you can appreciate how a BSS forms the foundation of a basic wireless network, and how more complex networks can be developed using this fundamental building block. Now that we understand how a basic wireless network is created and how a more complex wireless network can be created, let's have a look at how a user identifies a network. To allow other devices on the network to identify the access point, a Service Set Identifier, or SSID, is used. This is a name used to identify the network and is periodically broadcasted by the Wi-Fi device unless disabled. If it is disabled, a device will still be able to connect to the Wi-Fi network if they know the name, but the name won't be provided to them using a broadcast. If enabled, operating systems like Windows will display the SSID and allow the user to connect to the wireless network of their choice, assuming they are broadcasting the SSID. Using tools like packet sniffers, it is easy for an attacker to work out the SSID even if it has been disabled. There is much debate in the IT industry if disabling the SSID provides good security, since anyone with a small amount of skill will still be able to find it. Disabling the SSID does, however, prevent the casual person from finding it. SSIDs are great for users to use, but for devices to communicate with each other, a physical address is needed. The physical address is the Basic Service Set Identifier, or BSSID. The BSSID will be the physical address of the Wi-Fi router and is usually created from the MAC address. When you have two different access points that are linked together using the same SSID, a device using these access points needs a way to decide which of the two it wants to send data to. If the device moves between access points, the device may also want to swap access points to get better reception. In order to do this, each access point will generate a BSSID. This allows the device to simply send data to the access point it wants to use by using the appropriate BSSID. Some advanced APs may use multiple BSSIDs for features such as using multiple frequencies. When this occurs, the access point will create a second MAC address. How this is done is up to the manufacturer of the device. Some manufacturers may simply add 1 to the MAC address, while others use different methods to create a second BSSID. If you are doing Wi-Fi analysis, keep in mind that the access point may be using multiple BSSIDs, so don't limit your analysis to just the one, as you won't be getting all the traffic. Now that we have had a look at the basic building blocks that make up wireless networks, let's now have a look at what can affect them. Wireless signals as they are traveling can be absorbed or reflected. Two common materials known for their signal absorption properties are water and solid wood. Indoor aquariums or rooms with high humidity can reduce Wi-Fi strength. Other building materials, such as drywall, ceramic tiles, and brick, can also absorb Wi-Fi signals. Signals can also be reflected. Two common materials that reflect Wi-Fi signals are metal and reinforced concrete. While signal reflection might seem similar to absorption in terms of signal reduction, they have distinctly different effects. Absorption weakens the signal entirely, while reflection causes the signal to bounce back or bounce off in a different direction. This reflection can create a phenomenon called multipath fading, where the reflected signal arrives at the receiver slightly out of sync with the original signal. This phase difference can cause destructive interference, weakening the overall signal strength. Modern Wi-Fi technologies can mitigate these issues to some extent, but significant reflection from metal surfaces, mirrors, foil, and certain types of glass can still degrade Wi-Fi signal quality. Some materials have both reflection and absorption properties. For example, glass will both absorb and reflect Wi-Fi signals. The material and how thick it is can influence how it will affect the Wi-Fi signals. For example, tree leaves have both reflective and absorptive properties. So, depending on what time of year it is and how many leaves are on the tree, this can affect your Wi-Fi signal. You can see that where you place your Wi-Fi point can significantly increase or decrease your signal strength. But I will talk about that in a different video. Interference is unwanted signals that disrupt or weaken the Wi-Fi signal. Devices that can do this are other Wi-Fi networks, microwaves, and cordless phones, just to name a few. Interference decreases the reliability and speed of the Wi-Fi. Nowadays, everyone is using Wi-Fi, so there is a good chance your Wi-Fi network is close to another one. There are ways to reduce this interference. Let's have a look. Most Wi-Fi devices operate within the 2.4 GHz or 5 GHz frequency bands. The principle here is that higher frequencies change wavelength more rapidly from high to low compared to lower frequencies. This faster fluctuation in wavelength allows for encoding a greater amount of information. However, altering the wavelength also impacts other characteristics of the signal. The lower 2.4 GHz band offers greater range than 5 GHz. Essentially, the lower the frequency, the longer the distance it can travel. 2.4 GHz also offers better signal propagation. This means that it will go through walls and other obstacles better than 5 GHz will. There are some advantages to the 5 GHz range. Firstly, there are fewer devices in this range. The 2.4 GHz range is used for many other devices including Bluetooth, wireless keyboards, wireless speakers, microwave ovens, baby monitors, remote control toys, and security systems, just to name a few. The 2.4 GHz range is quite popular. When numerous devices operate on the same frequency, it becomes challenging to transmit data effectively. Imagine being in a room attempting to converse with someone on the opposite side. If it's just the two of you, the communication is straightforward. But if the room is crowded with people, all trying to talk across the space, the situation becomes much more complex. In such a scenario, your conversation would take longer as you navigate through the noise and interruptions. Similarly, in the world of Wi-Fi, this crowded environment translates to a slower rate of data transfer. The more devices competing for the same frequency, the more difficult and time-consuming it becomes to send and receive data efficiently. Lastly, 5 GHz offers more bandwidth than 2.4 GHz. Having a shorter wavelength means more data can be encoded. To summarize the distinctions, the 2.4 GHz frequency offers longer range transmission, though at slower speeds. Conversely, 5 GHz provides a less crowded spectrum with more bandwidth, enabling faster data transmission, but its range is shorter compared to 2.4 GHz. I haven't mentioned it earlier, but the latest Wi-Fi standard also includes support for the 6 GHz frequency band. Similar in characteristics to 5 GHz, the 6 GHz band offers a higher frequency, which equates to greater bandwidth, but reduced signal range. However, the difference between the two is relatively minimal. The primary advantage of 6 GHz lies in significantly lower congestion compared to 5 GHz. Several strategies are employed to enable multiple wireless devices to effectively share the same frequency band. Let's have a look. Wi-Fi uses multiple channels to help with congestion. A channel is a segment of a frequency band. Essentially, the frequency is divided up into small parts. Shown here is an example of the 2.4 GHz frequency divided up into different channels. Not all the channels shown are available in all countries. Each country has different regulations on which frequencies are allowed to be used. Some Wi-Fi routers will automatically change channels based on congestion, assuming the router is configured to auto. Otherwise, the channel can be configured. For a lot of routers, the default channel will be set to 6. You can see in this example router, the channel is set to auto. Also, the currently used channel is 4. The router will automatically change channels as required. I could, if I wanted to, set the channel manually. This router supports channels 1 through 11. In order to get better speed, some newer Wi-Fi standards support multiple channels. If your router supports it, the router can use multiple channels to communicate with devices. When looking at the channels, you will notice that the channels overlap. Thus, the most popular channels generally are 1, 6, and 11. Channel 14 is only used in Japan, so you won't find it in other countries. Now that we understand a bit more about how wireless works, let's have a look at how signals are transmitted in order to get better results and reduce interference. When it comes to wireless transmission, the amount of power utilized is subject to regulatory limits. It is possible to decrease the power output of your router if it supports this feature, but exceeding the regulated limit is not permissible. You may get an exam question testing your understanding of the implications of reducing a Wi-Fi router's power. Lowering the power output diminishes the range of the signal, potentially limiting its spillover into nearby areas such as public unsecured areas like adjacent car parks. However, this also means a reduction in signal strength for your users. Keep these considerations in mind when addressing questions related to adjusting the power settings of Wi-Fi routers. To make better use of the signal transmission, you can focus what you have. Here, the antenna will focus the signal in a certain direction. For example, the antenna may have material behind the antenna to reflect the signal in the opposite direction and block any other signals from entering. It is easier to understand with an example. You can see here the example of a cell phone tower. Although this is not a Wi-Fi example, the principles are the same. Cell towers use a rectangular box which contains small signal transmitters. The box is designed to transmit to a particular area called a sector, hence the name sector antenna. The antenna is specifically engineered to direct its signal in a particular direction. Each little transmitter has a motor which can adjust the angle by a small amount. They are built with materials that obstruct wireless signals entering from the rear. This design ensures the transmission occurs primarily in one direction while blocking incoming signals from the opposite side. Due to this focused transmission, the antenna works at a specific angle directly in front of the antenna. To get 360-degree coverage, multiple antennas are arranged in a circular formation. You can understand now why you see cell towers designed this way. The main takeaway from this is, when optimizing Wi-Fi performance, direct your signal where it is needed and reduce interfering signals. Doing this can significantly enhance the quality of your Wi-Fi connection. Improving the signal quality makes the Wi-Fi more reliable and increases the bandwidth. The best way to direct the signal is by choosing the right antenna. Omnidirectional antennas are the most common. These antennas broadcast in 360 degrees around the antenna. Since these radiate signals around 360 degrees, they are good for small buildings, including those that have multiple levels. When you start looking at Wi-Fi antennas, you may see some marketed as high gain. High gain focuses the wireless signal in a particular direction. This amplification increases the signal strength in that direction, effectively extending the range of the Wi-Fi network and improving reception. In the case of omnidirectional, if you see an antenna marketed as high gain, this means the wireless is being focused in a horizontal direction. Since the wireless signal is focused, this solution is good for horizontal buildings or large horizontal areas. There are also other Wi-Fi antennas designed to transmit in a particular direction. For example, ceiling antennas. Due to their elevated position, this allows the signal to travel further and penetrate obstacles more effectively in certain circumstances. They work best when placed in an elevated position that is unobstructed. There are also panel antennas which broadcast horizontally in one direction. These are good for outdoor areas like parks, streets, corridors, or tunnels where you want to provide coverage in a particular area. They can also help reduce interference since they are sending all the signals in one direction. The next type are long-distance antennas, for example, the Yaga-Uda antenna. They are often used for point-to-point links. For example, if there are two buildings quite a distance apart and you want to network them together. In some cases, it may be too costly or impractical to run physical cables between the two buildings. A Yagi-Uda antenna needs to be correctly aligned in order to work effectively. The final type to consider is the parabolic antenna. Operating similarly to the Yagi-Uda antennas in that they focus the wireless signal, their primary application is in point-to-point communication. The key distinction lies in the parabolic antenna's ability to focus the wireless signal more intensely than Yagi-Uda, enabling the signal to travel even greater distances. This highly focused beam, however, also means that parabolic antennas are more challenging to install, requiring precise alignment in their directional orientation. Additionally, parabolic antennas typically come with a higher price tag compared to Yagi-Uda antennas. You can see that one way to get better Wi-Fi signals is by choosing the right antennas. Your Wi-Fi network may also consist of multiple access points spread out over an area with different antennas. In upcoming videos, I will explore how you can effectively determine the optimal placement of Wi-Fi access points and conduct a site survey. This will help you assess whether you've made sound decisions in positioning your access points and selecting the appropriate antennas. There have also been a number of improvements in Wi-Fi that allow more data to be sent. Wi-Fi channel bonding is a technique that combines two or more adjacent Wi-Fi channels into a single wider channel. This can provide significant increases in bandwidth and overall network performance. In Wi-Fi's early days, each channel could support a maximum data rate of 54 megabits per second. As demand for Wi-Fi bandwidth increased, channel bonding was added to allow multiple channels to combine into wider channels, significantly increasing bandwidth. The bandwidth available with channel bonding is influenced by various elements, such as environmental conditions, network user density, and the kinds of devices connected to the network. Another way Wi-Fi bandwidth can be increased is by using MIMO, or multiple input, multiple output. MIMO allows multiple antennas to transmit and receive data at the same time. If your devices support it, it can use multiple antennas on the Wi-Fi router for transmitting and receiving data. For example, a device could use an antenna to transmit and then receive traffic on another antenna. The device could also use two antennas for sending and receiving data, thereby doubling its bandwidth. The maximum number of antennas supported is dependent on the wireless standard. It is up to the manufacturer of the Wi-Fi router and the manufacturer of the device to decide how many antennas they will use. So now you know why some Wi-Fi routers have so many antennas. Those with more antennas will cost more, but if your devices support it, you will get better performance. Another way that modern Wi-Fi also improves performance is beam forming. Beam forming is when the Wi-Fi is focused towards the device. Essentially, the signal is directed toward the device and the device directs the signal toward the Wi-Fi access point. Doing this reduces the interference between devices and other Wi-Fi. This image offers a simplified depiction of how beam forming is achieved. In reality, beam forming is a complex process and involves multiple antennas using constructive interference, phase shifting, and various other advanced techniques. It also requires careful consideration of numerous factors, including environmental influences. It also does not give you a perfectly shaped signal like the one shown. The key point to understand is that beam forming effectively focuses the Wi-Fi signal to a certain degree, though the underlying science behind it is quite complicated. I would not worry about the details, just understand that it improves performance and reduces interference by focusing the beam in a particular direction. In the realm of wireless connectivity, Wi-Fi has undergone a remarkable evolution. Upgrading your access point and devices will unlock a world of blazing speeds and seamless connectivity. In its infancy, Wi-Fi offered a mere 11 megabits per second, a speed too sluggish for serious work. Today, Wi-Fi has transcended those limitations, soaring to gigabit speeds that effortlessly handles even bandwidth-demanding tasks. So seamless is the transition between wired and wireless connectivity that an accidental disconnection from wired to Wi-Fi could go unnoticed. Embrace the transformative power of modern Wi-Fi and experience the pinnacle of wireless performance. Modern Wi-Fi access points can automatically select and optimize channels, freeing you from the complexities of manual configuration. Most modern Wi-Fi access points are set and forget. Put the device on automatic and only change the settings if you need to. If you have problems with your wireless signal, you may need to reposition your access point, tweak or replace the antennas, or consider introducing additional wireless access points to eliminate weak or black spots on your wireless network. In forthcoming videos, we delve deeper into Wi-Fi, looking at the standards, installation, and performing wireless surveys. Wi-Fi is here to stay. I hope this video has helped you understand Wi-Fi better. I look forward to seeing you in our upcoming Wi-Fi videos. Until the next video, I would like to thank you for watching.